Usually, when we talk about a software deployment, there is this expectation of a quiet, almost invisible precision, like hitting a light switch.
Right, it's expected to be binary.
Yeah, exactly. You push some code, a progress bar fills up on your screen, maybe a Slack notification pops up in a channel, and the team just points and says, there it is, it's live.
It's this clean, sterile process. And it happens on a server farm somewhere in the dark, miles away from anyone's actual desk.
Totally. It's comforting because it's hidden. We'll like our technical complexities to stay safely behind the curtain, right?
We definitely do.
But what if we rip that curtain down? Like, what if that quiet deployment isn't happening on a silent server, but is instead happening at 200 miles per hour?
That changes the math completely.
It really does. Imagine a physical, mechanical, and computational landscape that just completely shatters that illusion of quiet precision.
Yeah.
Because when you look at the world of high-performance engineering, specifically Formula One racing, you realize that our standard way of pushing code is not just quiet, it's dangerously passive.
It's a brilliant juxtaposition, honestly. Formula One is the absolute definition of a high-stakes engineering crucible. There is no curtain to hide behind when things go wrong.
Exactly. So welcome to the Deep Dive. Today, we are exploring the operational blueprints of what is arguably the most quality-obsessed engineering organization on the planet.
And we're doing it through the lens of this phenomenal framework put together by a lead software development engineer in Test, an SDET.
Right, an engineer with over 8 years of experience building quality systems. And not just any systems. We're talking FDA-regulated medical devices, payments at scale, aviation, and complex AI implementations.
That background is the vital context for this entire conversation. I mean, when we talk about FDA-regulated medical devices or aviation software, we are talking about code where the cost of failure isn't just a frustrated user clicking refresh.
Right, it's literal life and death.
Exactly. The cost can be catastrophic. So when an engineer from that world, someone who builds safety-critical systems for a living, looks for the ultimate model of quality assurance and points to a motorsports team, we need to lean in and ask why.
Okay, let's unpack this. Our mission today is to extract the highly reproducible patterns that make Formula One work.
The operational secrets.
Yes. We're going to figure out how you, listening to this right now, whether you're managing a remote dev team, running a startup, or just trying to get your weekend project to stop crashing, how you can apply these exact secrets to your own work.
And the best part is you don't need a $100 million F1 budget to do it.
Which is key.
Right. That is the most actionable piece of this. We aren't talking about buying wind tunnels for your tech startup. We are talking about mindset, process, and discipline.
So true. The patterns F1 teams use aren't romantic. They aren't science fiction. They are purely operational.
Purely operational.
Let's start with the sheer extremity of this environment. Why Formula One? I mean, why not NASA? Why not a nuclear submarine program?
It comes down to the frequency of iteration combined with the visibility of the outcome.
Okay, what do you mean by that?
Well, NASA engineers incredible systems, obviously, but they don't have to redesign the space shuttle from scratch every single year and then race it against 10 other space shuttles every Sunday.
Oh, that's a great point. The cadence is totally different.
Exactly. Formula One operates at the absolute edge of what physics, human endurance, and strict regulatory frameworks permit. And they do it on this relentless weekly cadence.
Let's put some numbers to that, because the numbers are just staggering.
They really are.
A modern F1 car utilizes a 1.6-liter hybrid power unit. Now, for anyone who isn't a gearhead, 1.6 liters is roughly the size of the engine you'd find in a standard commuter car, like a Honda Civic.
Right, a tiny little engine.
But in F1, that tiny engine block is producing over 1,000 horsepower.
It's absurd. Think about the heat, the vibration, the sheer violence happening inside that block of metal. It is an incomprehensible level of energy density. And to manage that stress without the engine just melting into a puddle of slag, the car is constantly communicating with the engineering team. The telemetry streams at 1,000 data points per second.
1,000 data points every single second.
Yeah.
And the chassis, the aerodynamics, the power unit integration,
Yeah.
it is all redesigned from scratch every single season just to comply with new regulations.
So if you want to translate that to a software engineering environment, imagine your CTO walking into the room and saying, hey, we have to rewrite our entire monolithic application from the ground up every 12 months.
Oh man, the panic that would cause.
Right. And by the way, it has to perform better than last year's version. It has to be flawless on day one. And if it fails, our company's stock drops in real time.
Okay, hold on. Let me push back here for a second.
Go for it.
Because if I'm an engineering manager listening to this, I'm probably thinking, look, I'm building a B2B SaaS platform. I'm updating a shopping cart interface. Comparing my Wednesday afternoon bug fix to a multi-million-dollar race car is a bit dramatic, isn't it?
Sure, it sounds extreme. Like, most of us aren't shipping code that can literally crash into a concrete wall at 200 miles per hour.
It's a completely fair objection. I mean, if we focus solely on physical danger, the analogy breaks down immediately.
Right.
But the core argument here isn't about physical danger. It is entirely about the visibility and the cost of failure.
The visibility. Unpack that for me. What does that look like in software?
Well, in standard software development, the cost of a bad deployment is almost always hidden, at least initially.
True.
You push a bug to production, and what happens? Maybe the database queries get a little slower. Maybe a few edge case users get a 404 error page.
Right, a silent failure.
Exactly. You, sitting at your desk, might not even know it happened until a customer takes the time to write a complaining support ticket 3 days later. The failure is insulated.
Yeah, if a server crashes in a forest and Datadog does an alert on it, did it even make a sound? Right. But in Formula One, there is zero insulation. Failing in production means your engine physically erupts in a massive cloud of white smoke on lap 3. Live. In front of 100 million people watching on television.
Wow, 100 million.
The sponsors who pay tens of millions of dollars to be on the side of that car see it. The rival teams see it. The fans see it. There are no silent failures in F1.
That pressure is just unimaginable. You can't just quietly roll back the code, clear the cache, and pretend the engine didn't just explode. You are entirely naked in front of the world.
You are. And because F1 teams cannot afford those hidden, delayed costs of failure, they have been forced by sheer survival instinct to develop patterns that guarantee reliability before the green lights go out on Sunday.
They cannot leave anything to a we'll-fix-it-in-post mentality.
Never.
Which means they have to know exactly what is going to happen before the race even begins. And that takes us directly into their first major operational secret. Simulation is discipline, not discovery.
Yes. This is where we see a massive divergence between how software is traditionally built and how high-stakes engineering actually operates.
Let's look at the track preparation. Before an F1 car turns a single real physical lap at a Grand Prix weekend, the team has already run hundreds, if not thousands, of simulated laps.
And we're talking incredibly deep simulation. They use computational fluid dynamics, or CFD.
For those unfamiliar, what does that actually entail?
CFD is essentially a massive supercomputer simulating how millions of individual air particles will flow over the specific microscopic curves of the car.
So it's basically digital wind.
Digital wind, exactly. And once they finish with the digital wind, they move to the physical wind tunnel. They will run exhaustive physical scale model sessions until they literally max out the hours allotted to them by the FIA, which is the governing body of the sport.
They push the testing to the absolute regulatory limit.
Every single time.
And it goes way beyond just the aerodynamics too, right? They put the actual driver, the human being, into a hydraulically articulated simulator.
Oh, yeah. It's a massive rig that physically moves. It pitches and rolls to mimic the exact G-forces, the specific bumps of the track they are racing that coming weekend, and it's matched to the forecasted weather and track temperatures.
So by the time the real practice session begins on a Friday afternoon, the team isn't wondering how the car will behave. The real practice session is merely a verification of what they already know.
Exactly. It is not a discovery phase.
Verification, not discovery. That distinction changes the entire engineering mindset, doesn't it?
It changes everything. They are not putting the car on the track to find out what will happen. They are putting the car on the track to confirm that their incredibly detailed mathematical models of reality are correct.
Right.
If the car behaves differently on the track than it did in the simulator, they don't just tweak the car. They immediately investigate why the simulator was wrong in the first place.
Now, let's hold up a mirror to the software industry. How does this look for a standard dev team? You know the drill. A team builds a feature on their local laptops. They push it to a staging environment. And let's be totally honest about staging environments. They rarely look exactly like production.
Almost never. I mean, they are usually scaled down, sanitized versions of reality. They completely lack the chaotic, noisy, malformed data of real users. They don't have the same load.
Yeah, exactly. So the team runs a happy path demo.
The happy path.
Always the happy path. The product manager clicks through the feature exactly the way it was designed to be clicked. Everything looks great. So they ship it, they merge to main, they push to production. And then everyone acts completely shocked, like utterly bewildered, when the production database locks up because it gets hit with complex concurrent traffic that staging never saw.
It is a fundamental mismatch in expectations. Software teams routinely use production as their discovery phase. They ship code to discover how it will actually behave in the wild.
It's like building a race car, driving it around an empty supermarket parking lot at 20 miles an hour, carefully navigating around a few stray shopping carts.
Right, avoiding the carts.
Yeah, and then confidently assuming you are 100% ready to take the hairpin turns of the Monaco Grand Prix at full speed. It's absurd.
The parking lot analogy is painfully accurate, but it raises a really important structural question for the industry. Like, why do software teams do this? Is it a tooling problem? Do we just not have the equivalent of a wind tunnel for software?
That is the crucial question. Are we just lacking the tech?
No, we absolutely have the tools. We have chaos engineering platforms, we have shadow traffic, we have massive load testing suites and complex replay frameworks. The tools have existed for years.
Okay, let's break some of those down because they are fascinating. Chaos engineering. What does that actually mean in practice?
Chaos engineering is the practice of intentionally injecting failures into your systems just to see how they respond.
Like breaking things on purpose.
Exactly. Imagine a program running in the background of your infrastructure that randomly shuts down servers, severs network connections, or spikes CPU usage. The whole goal is to prove that your system is resilient enough to handle unexpected outages without the user ever noticing.
It's like having a gremlin in the engine just unplugging wires to see if the backup systems kick in. I love that. And what about shadow traffic? That's another great concept.
Shadow traffic is brilliant. Say you are rewriting the core payment processing engine for your app. Instead of just flipping a switch and hoping the new code handles the live credit card transactions properly, you use shadow traffic.
Okay, how does that work?
You take the live stream of real user requests and you send them to the old reliable system so the user gets a seamless experience. But you simultaneously send a copy of those exact same requests to your new unreleased system.
Oh, the shadow.
Exactly. The new system processes the transaction, but its output goes nowhere. It's just logged. Then you compare the logs. Did the new code calculate the tax correctly? Did it handle the database lock the same way as the old code?
So you are testing with the messy reality of live production traffic without risking a single user's experience.
Yes, you're verifying against reality.
So we have digital wind tunnels. We have the tools to simulate reality perfectly. So if it's not the tooling, why is software so uniquely prone to skipping this?
It comes down to discipline and incentive structures. F1 teams treat simulation as a mandatory, unskippable discipline because, as we established, shipping the wrong setup is explosive in public.
Right.
Software teams, on the other hand, often treat rigorous simulation like load testing or running shadow traffic as an optional luxury. It's something you do if you have a little extra time at the end of a sprint.
And if you've ever worked in tech, you know there's never extra time at the end of a sprint. The product manager is always pushing for the next feature.
Exactly. Rigorous simulation is often the very first thing cut when a deadline looms. In F1, cutting your simulator time because you're running late would be considered gross engineering malpractice. In software, it's just called agile delivery.
Oh, wow. That hurts because it's true. Okay, so that's a massive shift in mindset. Treating simulation not as a nice to have, but as the core discipline of deployment. Well, let's push the scenario forward.
Sure.
Let's say you do the simulation. No matter how incredible your CFD models are, no matter how many hours your driver spent in the hydraulic rig, the real world is messy.
Entropy always wins.
Right. The track temperature spikes by 10 degrees. A rival car drops a piece of carbon fiber debris on the racing line. The wind shifts. Live traffic is fundamentally unpredictable.
Very unpredictable.
So when the lights go out and the race starts, how do F1 teams handle live, unpredictable anomalies? And how does that compare to us just staring at our server dashboards?
This brings us to the second operational pattern, real-time telemetry, and crucially, active monitoring.
Let's look at the car itself first. An F1 car runs around 300 distinct sensors. We are talking about sensors monitoring tire core temperatures, hydraulic brake pressure, aerodynamic load on the front wing, the exact mixture of fuel and air in the combustion chamber.
And these sensors are streaming data at 1,000 hertz
1,000 times a second.
back to the pit wall at the physical track, and simultaneously via satellite to the team's mission control, which might be thousands of miles away in a factory in the UK.
But here is the critical distinction. They don't just have all this data flowing into a giant, colorful dashboard that everyone casually glances at while sipping coffee.
No, not at all. A senior engineer is paid to watch specific signals live.
This is the vital difference between active and passive monitoring. If a specific parameter, say, the hydraulic pressure in the rear braking system, drifts even slightly outside its expected mathematical envelope, that engineer is on the radio to the driver in under 5 seconds.
Under 5 seconds.
Yeah. Turn 4, shift your brake bias forward. We are seeing a pressure drop. Immediate, actionable intervention.
Now, I can hear the seasoned developers listening right now saying, wait, we have telemetry, we have countless monitoring tools, we use Datadog, we use Splunk, we have massive TVs mounted on the wall in the engineering pit showing beautiful Grafana charts. How is this F1 setup any different?
Right, it sounds the same on paper.
But having a dashboard is not the same as having a system of active ownership. What's fascinating here is that the F1 system is not defined by the presence of a screen.
What is it defined by?
The system is defined by human accountability. It's not, we have dashboards, it is. A highly trained human is explicitly paid to watch this one specific signal, and they have the authority to take immediate action if it deviates.
Active ownership versus passive observation.
Exactly. In the software world, we suffer deeply from dashboard blindness. We have hundreds of beautiful time series graphs, but nobody is truly accountable for staring at them continuously during normal operations.
Yeah, alerts fire off constantly, like CPU spiked for 3 seconds, memory usage is at 80%.
And because there's so many of them, engineers suffer from alert fatigue.
Oh, the muted Slack alerts channel. Every tech company in the world has one. It's just a scrolling graveyard of automated panic that everyone ignores because, it always does that.
Right. It always does that is the most dangerous phrase in engineering.
Absolutely.
Because of that passive, noisy environment, real regressions and severe bugs are usually not discovered by our sophisticated monitoring tools. They are discovered via user bug reports.
Think about how backwards that is.
Yeah.
The person paying you for a service becomes your telemetry sensor. That is the most expensive and damaging way to find out your system is failing.
Which is bad enough for traditional software. But this framework takes this concept of active telemetry and applies it directly to the biggest, most disruptive shift in our industry right now.
Here's where it gets really interesting. You're talking about artificial intelligence.
Yes. This is where the classical QA model entirely fractures, and where the F1 telemetry model becomes absolutely mandatory.
Let's unpack the classical QA model first. The way we have tested software for decades is highly deterministic. You write a unit test. You say, when I feed the number 2 and the number 2 into this function, the output must be 4. You run it in your continuous integration pipeline, your CI/CD process, that builds and tests the code automatically. If the output is 4, the test passes.
The light turns green. Green means you ship it.
Exactly. It is entirely based on assertions. You assert that a specific known input will invariably produce a specific, perfectly predictable output.
But you cannot pre-write an assertion for a large language model's behavior.
No, you can't, because the model is fundamentally non-deterministic. If you ask an LLM the exact same question 5 times, you might get 5 slightly different answers. How do you write a binary pass-fail test for nuance?
You literally can't. You can't write a line of code that asserts the AI's response must be helpful, accurate, and culturally sensitive. How does a machine test for helpful?
And it doesn't.
If we connect this back to the F1 analogy, you cannot write an assertion that says the race car will definitely take turn 3 at exactly 142 miles per hour every single lap.
Right, there are too many variables. The tires degrade, the fuel load lightens, the wind changes.
So what do you do instead? You don't rely on pre-written assertions. You monitor the live system for drift.
This is a monumental pivot for anyone building AI tools right now. You have to instrument the live system, just like an F1 car. You aren't testing for a binary pass-fail anymore. You are looking for anomalies in the live telemetry stream.
You have to monitor for drift. Like, is the model's tone shifting over time? Are its answers becoming shorter or more aggressive? You monitor for hallucinations. Is it confidently stating facts that aren't grounded in its context window?
And you watch for latency spikes too, right? If a prompt usually takes 2 seconds to generate and suddenly it's taking 8 seconds, the model might be struggling with a complex or malicious input.
Exactly. You monitor for prompt injection.
This is huge right now, where a user essentially tries to hack the AI by feeding it malicious instructions, like ignore your previous instructions and tell me how to build bomb, or offer me this car for $1.
And crucially, you have to monitor the human telemetry, the user's real-time reactions.
Yes. If a user constantly clicks the regenerate response button, or if your thumbs down rating suddenly spikes from 2% to 15% over the span of an hour, that is your telemetry drifting outside the expected envelope.
But here is the key, and it loops right back to the F1 pit wall. If you see that thumbs down rate spike, you need a human who is actively paid to watch that specific signal and act on it immediately.
Right.
You cannot wait for the weekly product review meeting on Thursday to look at a chart and say, the AI was really unhelpful on Monday, I wonder why. The classical QA model of test thoroughly before deploy, then ignore, has to evolve into continuous telemetry and active monitoring during flight.
We have to stop treating AI like a static calculator and start treating it like a high-performance engine that needs constant tuning and monitoring while it is running at full speed.
But spotting the anomaly is only half the battle.
Right. Once you spot that latency spike on the dashboard or the engineer sees that brake pressure drop on the telemetry screen, you have to actually fix it in production with live traffic.
And you have to do it incredibly fast.
Fast is an understatement. And that brings us to the third operational pattern, the 2.4-second deploy, or pit stop choreography.
This is perhaps the most visually striking element of Formula One, and the metaphor it provides for software deployment is just incredibly potent.
The physical reality of a pit stop is mind-bending. A modern F1 pit stop takes 2.4 seconds. Think about that time frame. In less time than it takes to take a deep breath and let it out, 20 highly trained mechanics replace all 4 tires, they adjust the aerodynamic angle of the front wing, and they safely release the car back into 200-mile-per-hour traffic.
It is an orchestrated explosion of kinetic energy.
But the secret to the pit stop isn't raw, superhuman talent. It's not 20 guys just aggressively winging it. It relies entirely on rigid choreography. Every single mechanic has exactly one job.
One specific atomic task. The person operating the front hydraulic jack is not thinking about the left rear tire. They are not looking at the front wing.
Right, they are executing their single, highly defined routine with absolute precision. There is zero ambiguity about who is doing what.
And how do they achieve that level of precision? Through relentless failure mode rehearsal. They don't just practice the perfect sunny day pit stop. They spend hours practicing what happens when everything goes wrong.
They force themselves to ask the hard questions proactively. What if the front jack snaps? What if the pneumatic wheel gun jams and won't release the lug nut?
What if the driver locks up the brakes and overshoots the painted pit box by 3 feet?
They have a rehearsed muscle memory response for every single one of those failures. If the front jack fails, a backup mechanic is already stepping in with a secondary jack before the primary mechanic has even dropped the broken one.
And here's the kicker, the thing that separates F1 from almost every other industry. They run a comprehensive review after every single stop.
Not just the bad ones. Not just the ones where they dropped a tire. Every stop.
Now, compare that choreography to the average software deployment. If you're a developer listening to this, prepare to wince because we've all been here.
Yeah.
How does a standard deploy look?
Oh, man. It usually involves a single engineer, possibly working late on a Friday.
The worst time to deploy.
Right. They merge the code, the CI/CD pipeline runs, hopefully it passes without any flaky tests failing randomly. Someone hits the big deploy to production.
And if something breaks, it's pure, unadulterated chaos.
Total chaos. The site goes down, alarms start blaring in Slack, the whole team scrambles onto a frantic Zoom call. 5 different engineers are looking at 5 different log files, talking over each other, trying to improvise effects or figure out how to write a database rollback script on the fly.
There is no choreography. There are rarely any detailed runbooks for the specific failure mode that just occurred. There is zero rehearsal. No one spent Tuesday afternoon practicing what to do if the new database migration accidentally locked the primary user table.
And reviews. Postmortems. In standard tech culture, those only happen if something catastrophic caught fire. The site was down for 3 hours, and the CEO demands a written explanation.
This brings up a profound psychological shift that F1 teams have mastered, which software teams desperately need to internalize. F1 teams review even the incredibly successful pit stops.
Which seems counterintuitive. Like, why review a 2.4-second stop? It was flawless. You didn't lose any time. High fives all around, right?
Because the driving question for an F1 team is never, did we get away with it?
Oh, man, did we get away with it? That is exactly how software teams feel after a sketchy deployment. We shipped it. The site is technically still up. My heart rate is 150 beats per minute. Thank God it's over. Let's go to the pub.
Exactly. We view a successful deploy as dodging a bullet. We survived the Russian roulette of pushing to production. But F1 teams ask a completely different, much healthier question.
Which is
this a system we can reliably execute together under immense pressure every single time?
wow. They review the perfect stop to understand exactly why it was perfect, so they can guarantee they can reproduce it.
Yes. They are looking for micro variations. Maybe the left rear wheel gun engaged 1/10 of a second slower than the right rear. It didn't cost them the race today, but if they don't fix that pneumatic pressure variance, it might cost them the championship tomorrow.
That is the essence of choreography over improvisation. In software, we rely far too much on the heroic improvisation of senior engineers to dive in and save us when a deploy goes bad. We praise the firefighters.
F1 doesn't want firefighters. F1 relies on the boring, rehearsed reliability of the system.
So to get away from firefighting, you have to anticipate failure. You have to rehearse the wheel gun jamming. But to do that, to sit in a conference room with your peers and say, hey, what happens if my code completely takes down the billing API, requires a very specific kind of team environment.
It requires an environment where people are not terrified to admit that their work might fail or that they themselves might make a mistake.
Which means we are no longer talking about servers and code. We are talking about human psychology. And that leads us to the fourth operational pattern, the cultural backbone, or what we'll call ruthless, blameless mining.
This is where we move from the mechanical processes, the simulation tools, the telemetry dashboards, the deployment pipelines, into the deeply human element of quality engineering. You can have the best CI/CD pipeline in the world, but if your culture is toxic, your quality will degrade.
In Formula One, there is a concept called a DNF. It stands for did not finish. Your engine blew up, your hydraulics failed, or your driver put the car into the wall. You are out of the race. 0 points. It is the worst possible outcome for a team on a Sunday.
It is a massive, highly public, and incredibly expensive failure.
But the reaction to a DNF is what separates the elite from the rest. When a car suffers a catastrophic failure and rolls to a halt, the team's first response, the very first question asked over the radio or among the engineers in the garage, is never whose fault is this?
Never. That is a crucial cultural boundary. The initial inquiry is strictly firewall separated from assigning individual blame.
Instead, the immediate instinctual reaction is, what data did we have and what did we miss?
They do not frame a DNF as a shame event. A DNF is immediately reframed as the most expensive data point of the entire weekend. The team just spent millions of dollars to discover a flaw in their complex system, and they are going to mine that flaw ruthlessly to ensure it never, ever happens again.
The most expensive data point of the weekend. Let's contrast that with standard tech culture, because this is where I think a lot of teams get it horribly wrong.
There's a toxic second-order effect in much of the software industry regarding how we handle bugs and outages. In many organizations, bugs are treated fundamentally as failures of individual attention or competence.
Oh yeah, who wrote this code? Who approved this pull request? Why didn't QA catch this? It becomes an immediate witch hunt.
Exactly. Bugs are inherently tied to personal shame and professional status. If you write buggy code, you are viewed by management as a lesser engineer. You might get passed over for promotion.
And what happens to human behavior when bugs equal shame?
Human nature takes over, self-preservation kicks in, engineers learn to hide their mistakes.
It's just self-defense.
Right. If a developer discovers a critical flaw in their own code right before a release, instead of flagging it and halting the release, which would draw negative attention to themselves, they might quietly try to patch it under the radar. Or worse, they push it through, cross their fingers, and hope it doesn't trigger in production.
They protect their personal status at the expense of the entire system's integrity.
Yes. And when a team it becomes corporate theater.
Corporate theater, yes. The dashboards stay beautifully clean. The CI/CD pipelines stay bright green. Management looks at the metrics and thinks everything is perfect, but it's a lie. It's what the industry sometimes calls watermelon status.
Green on the outside, bright red on the inside.
Wow, watermelon status. I haven't heard that in a while, but it's so accurate.
The system is actually rotting from the inside out, but nobody's saying anything because honest assessment has become politically and socially too expensive for the individual. The organization punishes honesty, and ultimately, the quality of the product pays the ultimate price for that silence.
F1 teams understand that if a mechanic is afraid to say, hey, I accidentally dropped a 10-millimeter wrench near the air intake and I can't find it, the engine will literally blow up at 200 miles per hour. Psychological safety is often talked about as a soft, fuzzy HR concept in the tech world, but in high-stakes engineering, psychological safety is a hard, non-negotiable engineering requirement.
You cannot fix what your team is too terrified to surface.
Okay, we've covered a lot of ground here. We've talked about verifying instead of discovering. We've talked about active telemetry, choreographing deployments, and blameless culture. If you're listening to this, you're probably nodding along. You want this for your team. But you don't have an F1 garage. You have a Jira board, a bunch of remote developers on Slack channel, and a tight deadline.
Right, the reality of the daily grind.
So how do you actually implement this on Monday morning?
We need to bridge the gap between inspiration and literal Monday morning implementation.
Let's do it. This is the climax of our deep dive, the actionable playbook. We have 5 highly concrete steps. And what is most vital about these steps is that they require absolutely 0 new headcount and 0 new expensive enterprise software subscriptions. You can do this with the team and tools you have right now.
Let's take these one by one and really explore the mechanics of how a team executes them.
Step 1. Run one simulation together. Specifically, intentionally inject a single failure mode into your staging environment that has never been tested before. Watch what breaks and then talk through it blamelessly.
This is about building the muscle of safe discovery. Don't just click through the happy path. Get your team together on a call, open your staging environment, and do something destructive.
Artificially spike the latency on your third-party payment gateway by 500 milliseconds. What happens? Does your user interface fail gracefully and show a polite error message? Or does the entire front-end application crash and burn?
Or drop a database table in staging. See how long it takes the team to notice. And the talk through it part is the secret sauce. You aren't doing this to point fingers and say, ha, Sarah's front-end code broke. You're doing it to examine the brittle edges of the system.
Okay, when the database slowed down, the UI froze. How do we build a circuit breaker to prevent that?
It's controlled chaos to prevent uncontrolled chaos.
Love that. Step 2. Pick 5 signals, not 50.
Yeah.
Identify the exact vital signs that definitively prove a production regression and drop all the other noise.
This is the cure for dashboard blindness. If everything on your screen is red and screaming, then nothing is an alert. You need to identify the absolute heartbeats of your application. What are the 5 metrics that, if they fail, mean the business is actively losing money or trust?
Let's debate that. What makes a good signal versus a vanity metric?
Well, CPU usage is a vanity metric. If CPU spikes to 90%, but the user experience is fine, who cares? That's just the server doing its job. A real vital sign is a business level metric. Successful logins per minute, shopping cart checkout completion rate, error 500 rate on your core API, maybe database query latency for your heaviest transaction.
Okay, so you pick those 5, you put those 5 things, and only those 5, on a single clean screen. And during a deployment, you assign one specific human being to watch that screen.
Active monitoring.
Right. If the baseline checkout completion rate suddenly drops by 10% after the deploy, that engineer has the authority to halt the line. No debating, no let's wait and see, just immediate action. Active telemetry.
Precisely. Which leads directly into step 3. Choreograph the next deploy. Stop improvising. Document exactly who does what, in what order, and what the explicit fallback plan is.
What does a good runbook actually look like in practice?
It should look like a script for a play or a flight checklist for a pilot. It is highly specific and leaves no room for interpretation. At 14 munch hours, developer A merges the pull request. Developer B actively monitors the 5 vital signals on the dashboard. If the error 500 rate exceeds 2% for more than 1 minute, Developer C executes the rollback script located at this specific file path.
Everyone knows their lines. Everyone knows where the emergency exits are.
Exactly. It removes the panic. When production breaks, your IQ effectively drops by 20 points because of adrenaline. A run book does the thinking for you when you're panicking.
Okay, step 4. Run a post-deploy review. Take just 5 minutes after the next deploy, even if it goes perfectly, especially if it goes perfectly, to review the mechanics of the deploy itself.
This is the F1 pit stop review, and software teams often hate this idea. We just deployed, it works, let us get back to coding.
Right, why sit in another meeting? We have actual work to do.
Because you aren't reviewing the code, you are reviewing the machine that ships the code. You ask 3 simple questions. Did the CI pipeline run as fast as we expected? Were our 5 vital signals clear and unambiguous? Did anyone feel confused or rushed at any point during the deploy?
It takes 5 minutes, and it ensures you are continually refining a reliable execution system.
It's such a small time investment for such a massive payoff.
And finally, step 5. Schedule a deploy drill. Next month, pick a time with low live traffic and just run through the deployment and rollback steps to surface process gaps before a real production fire forces you to.
Rehearsal. How many teams have a rollback script they wrote 2 years ago but have never actually tested?
Oh, a terrifying number of them.
A deploy drill forces the team to look at the runbook, execute a rollback, and verify it works when their heart rate is normal. It is infinitely better to find out your rollback script has a permissions error on a quiet Tuesday morning drill than during a massive outage on Black Friday.
So we have these 5 steps. Simulate failure. Pick 5 signals. Choreograph the deploy. Review the process. Rehearse the rollback. If we zoom out and look at these together, what is the underlying philosophy we're trying to adopt?
The philosophy is that quality is not a checkpoint. It's not a toll booth at the end of the development cycle manned by a grumpy QA engineer. Quality is a shared operational practice built collectively by the entire team long before the code ever hits production. You cannot test quality into a poorly built system at the last minute. You have to engineer quality into the system's DNA from day one.
We've covered an incredible amount of ground today. We started by looking at the sheer extremity of Formula One to understand why they simply cannot afford hidden, silent failures.
We explored the crucial shift from reactive testing to proactive simulation, verifying what you already know in staging rather than discovering it the hard way in production.
We broke down active telemetry, and specifically, we highlighted the massive paradigm shift required for testing non-deterministic AI tools, where you have to abandon rigid test assertions and instead actively monitor for model drift, hallucinations, and real-time user reactions.
We looked at the extreme choreography of the 2.4-second F1 pit stop and the psychological necessity of reviewing even your successful deployments to build bulletproof systems.
And we unpacked the cultural backbone, the absolute necessity of psychological safety, treating failures not as shameful secrets to be hidden, but as wildly expensive data points to be ruthlessly mined without blame.
It is a complete operational and cultural overhaul. But as that 5-step playbook demonstrates, it is entirely within reach for any software team willing to commit to the discipline.
Before we sign off, we want to leave you with a final provocative thought, something to chew on when you log back into work tomorrow. Think about the concept of the DNF, the catastrophic crash that an F1 team views as the most valuable data point of their weekend.
Yeah, think about your own team's DNF.
Exactly. I want you to look back at the biggest bug, the most painful outage, or the worst system failure your team experienced this past month.
Ask yourself and be brutally honest. Did your team mine that failure for gold? Did you extract every single ounce of systemic learning from it? Or did the team quickly bury it in the dirt, patch it quietly, and move on as fast as possible to protect someone's ego or the team's status metrics?
If you changed just that one reaction, if you made it culturally safe to ruthlessly mine failure without a drop of personal blame, how different would your team's code and your team's stress levels look a year from now?
It would be night and day.
You know, at the start of this deep dive, we talked about the illusion of the quiet, invisible software deployment, the comforting light switch. But the truth is, the moment your code hits production, you aren't flipping a switch in an empty room. You are driving at 200 miles an hour, and your users are relying on you to keep the car on the track.
It's time we started engineering like it.
Thank you so much for joining us on this deep dive. Take these ideas, share them with your team, run a simulation this week, and we will see you next time.